All right, questions to hear? All right, so the force due to gravity, big G, or magnitude of force due to gravity, m1, m2 over r squared. Hopefully that can be seen well enough. So the question is, what is r? What does this represent?
Distance between mass 1 and mass 2? Is it the distance between mass 1 and mass 2?
Okay, let's narrow that down some. What is r right now between you and the Earth? Did you say 10?
No?
I thought.
Oh, I don't know, I said I
Oh. Anyway, what would r be between you and the Earth right now? Ballpark. I mean, I'm not pulling out a tape measure to find out if you're right or not.
1 floor.
You said 1 floor? Anyone wants to agree with her or disagree with her?
I'll agree.
You? Carrie's got your back. Anyone want to stand up and go, what were you thinking? I don't know if to take that as rousing support or not. All right, so let's assume that it is just surface to surface distance. So let's say you're standing, you go outside and you put your hand on the dirt. What would the distance be then?
0.
All right, but, you know, in reality though, I mean, there's some layer of skin there. I can't really divide by 0, so I'm just gonna make a small number. So let's assume that the top here, multiplied together, is mass of the Earth, my mass is, so let's just do the exponent part. So this is 10 to the negative 11th times the mass of the Earth, 10 to the 24th, my mass, 10 to the 2nd, divided by 0.000. Some tiny number. So on the top there, we have 10 to the 26th, 15th, so that's 10 to the 15th. And on the bottom, this is 1, 2, 3, 4, 5, 6, 7. So that's 10 to the negative 7th squared. So that's 10 to the 15th over 10 to the negative 14th, which is 10 to the 29th. Just order of magnitude. That's huge. If it were indeed surface to surface, if it were 1 floor or 10 meters or whatever, or 3 meters, whatever that distance is, that would be a huge force. So what's another speculation for what r could be? What distance is that?
From the center of the Earth.
Yeah. It's center to center distance. Technically, center of mass to center of mass. So this would be the force on you if you went out and touched the ground. You would never leave. You would touch the dirt and then you would stay there. Matter of fact, that force is so big, you would actually, if it were surface to surface distance, the gravitational force on your feet would be different than that on your head. It'd be like going inside the horizon of a black hole. I'd not say we wouldn't exist, but we would have evolved differently if we would have evolved at all. So if R is surface to surface. I think one of the homework problems talks about what's the acceleration of gravity of something that is in orbit at 100 kilometers, or 200 kilometers? It's one of those two. What do you say, 200 kilometers? G at altitude of 200 kilometers. So we have some satellite that's going around the Earth. What is the acceleration of gravity on it? Well, we can figure that out now. I know that the force due to gravity is equal to mg, which would be mass of the satellite, which is also equal to big G, mass of the Earth, mass of the satellite, over r squared. Now you can go through like we did last time, where we actually multiplied by the mass of the Earth to get the force, and then we divided by mass of the Earth to get the acceleration due to gravity. Or you can do it this way, and we can just cancel out mass of the satellite and just go straight to a formula for G, little g. This is big G, mass of the Earth, over the distance squared. So 6.67 times 10 to the negative 11th times mass of the Earth, 5.98, times 10 to the 24th, divided by the distance. Because this is center to center distance, and this altitude is from the surface, so r would be the radius of the Earth, about 6.38 times 10 to the 6th plus meters.
So is that always the same formula? Like the same numbers?
Which part?
The top part?
That's always the same. This one depends on what we're working with. When we were dealing with Earth, Sun, then we had mass of the Sun, mass of the Earth. Here we'll have mass of the Earth and mass of the satellite, which I canceled out. But it depends on whatever the two masses are. But this number here is always the same. I just do a lot of Earth problems, so that's why this keeps showing up. So Earth, radius of Earth, and then altitude. We say 200 kilometers, that's 200,000 meters. So plus 200,000.
Where did you get the 6.38?
The radius of the Earth.
Oh,
Yep, that, Hewitt has it written as 6.38 one place. No, he actually has it 6.37 here. Yeah, the average is actually 6.378137 meters. This number will float around some. I think Hewitt has 6.4 somewhere. It floats around because it really depends upon, are you at the equator or the poles? We're not a perfect sphere. And so the center to center distance answered your question, right?
yes.
Okay. So the center to center distance, we have to take into account the radius of the Earth plus whatever the altitude is. How far are we above our average plane on Earth? Please make sure you add it before you square. So this becomes 6.67 times 10 to the negative 11th, 5.98 times 10 to the 24th, divided by what will end up being 6.58 times 10 to the 6th squared. Because this right here, and we can go for the typical stunning visual effects, that's 0.2 times 10 to the 6th. Or if you're using the calculator will do it for you, as long as you don't add or miss the number of zeros there. Now, before we actually do the calculation, I guess Jay's working on it right now. So if you've already done it, just sort of hold back for a moment. If you are in the middle of it, just pause for a second. So the acceleration due to gravity where we are right now, 9.8 meters per second squared. If I go up 200 kilometers, 200,000 meters, how much of a difference do you think the acceleration due to gravity will be? Gut feeling. So this is your guess. Less than 4.9 meters per second squared. Less than 9.8 meters per second squared. And we'll just take a choice of two. If I go up 200,000 meters, would you expect the acceleration due to gravity to be less than half of what it is here, or just somewhere less than what we have here? So who thinks it's going to be less than half? One, two. Who thinks it's just going to be less than 4? Diane? Are you going? Okay. I wasn't forcing you one way or the other. Just. All right. So we got 5 people here, 2 people here. All right. So let's do the calculations now. So I guess, Rachel, from the look, you have an answer?
It's 9.21.
Anyone else get the same thing? Okay, got a couple other people with the same thing. Units?
Maybe kilometers?
Meters per second squared.
It'll be meters per second squared. It's a, did you fit? It sounded like you were in the middle. You stopped while you. I wasn't trying to ignore you. I thought you were halfway through your
No, I
answer.
said kilometers.
It's meters per second squared. The reason why it's not going to be kilometers is that this has meters in it, and we converted all these to meters. I guess we started out in meters. The textbook, got to be careful with that. The textbook, one place actually expresses the radius of the Earth in kilometers. So don't forget to move that decimal place over 3 if you want to put it into meters. So acceleration due to gravity, if you were that far up, it seems like a really far distance. I mean, airplanes fly at elevation of a mile or 2 up. So airplanes fly at around 3,000 kilometers up. So 200,000 kilometers up seems huge, but it's really not big compared to this size of the Earth. So if I did this closer to scale, 200,000 would be, basically right there. So on a relative scale, that's roughly where 200,000 kilometers would be. Ish. Questions to hear? All right. Now I know what really jazzes you up. Math. A bunch of letters on the board. So let's go do that, just to get you all pumped up. Now, we've talked about conservative forces. Chapter 6, I think it was. We did conservative forces. And the fact that gravitational force is conservative. So let's just start out with that. Gravitational force is conservative. We have talked about that every gravitational force has a potential energy formula. Therefore, it has associated potential energy formula. I am not going to derive the potential energy formula. It does require calculus well beyond the scope of this class. So I'm just going to sort of spoil it for you. Let's just sort of, if we're talking about weight is the conservative force, then the potential energy formula is mgh. That still holds. But we're going to be now dealing with a situation where this g, even though it might have some value, is going to change. So if I shot something way off into outer space, the value of little g is going to change. We've already done 2 of them. Misleading. So we have the value of g there. If we're talking about the generalized gravitational force, the formula is negative big G mass 1 mass 2 over r. Looks a lot like the force formula, except we got a negative in front and it's not squared.
And wait, what is that formula for?
That is the potential energy formula for the generalized gravitation. Because we need that in order to be able to figure out the size of black holes. Questions to hear? All right, so our scenario is I have some planet here. I'm just going to call it planet X. And I'm going to launch a projectile. I'm just going to label that S for, I guess technically it's not a satellite, so I'll label it P for projectile. I'm going to launch this projectile. And so I'm assuming it's at its maximum speed at the surface of the planet, and then after that it's going to start slowing down. So speed is at the maximum speed at surface. So any propulsion I have happens right there at the surface. As soon as it leaves the surface of the planet, there's no more propulsion, there's nothing else slinging it, it's just traveling under its own momentum. So the speed is the maximum. I guess I probably should be V max is equal to the speed at the surface. I'm assuming, because these are all assumptions, assume no interference with flight, for lack of a better term. In other words, there's no air resistance. It's not going to run into another planet or moon. It's just being launched, shot off into space. No interference with flight once launched. So the only force acting on it is the force due to gravity from the planet. So let's put this in smaller terms. I have a marker here that I throw up into the air. It goes up, it gets pulled back down. Actually, it's being pulled down the entire way up, which slows it down, and then it reaches the peak, and it still gets pulled down and comes back. What would happen if I threw this faster?
Same thing would happen at a faster speed.
Meaning?
satellite is still gonna be pulled down. And then whenever it reaches its peak, it's still gonna go to the floor.
Okay. In terms of the flight path, if I, toss it like that versus toss it faster, what's gonna be the difference in looking at it?
It'll be higher.
Yeah, okay, but it'll still get pulled down. So what I want to know is how fast do I need to shoot this thing so that it never comes back? Because here, if I'm just throwing an object, the pull back to the Earth is relatively the same. It's relatively constant. We know that if you get to 200,000 kilometers, the pullback is a little bit less. But the pull will get smaller the farther away from the planet it gets. And so we're trying to figure out at what speed will be so that it never actually comes back. And to do this, we need to do conservation of energy, because the only force acting on it once it's launched is the force due to gravity, which is conservative. Energy is conserved. In other words, the initial energy is equal to the final energy. And we have two types. What are the two types of energy involved here?
Potential.
And yep, that's it. So we have initial kinetic plus initial potential equals final kinetic plus final potential. Oh, you know what's coming next. Get yourself mentally prepared. What is the formula for kinetic energy? A little less enthusiasm than I was hoping. Let's do it again. What the heck? What's the formula for kinetic energy? Didn't want to do it this time. This is mass of the satellite squared plus potential energy formula, which is that one right there. So minus big G, mass of planet X, mass of the satellite over the initial distance, equals 1/2 mass of satellite V final satellite squared minus big G, mass of X, mass of satellite over R final. So it's the same thing we did before, like the ski slope problem. The only difference is I have a different formula for potential energy. And it might seem daunting right now, but we can get rid of some stuff. So I ask you, what can we get rid of?
The satellite.
Oh, because it's in every term? We do have mass of satellite in every single term, so we can multiply by the reciprocal of it or divide by mass of the satellite, so that will go, we can get rid of that. Simplifies it a little bit. What else can we get rid of?
Big G.
The big G?
Uh-huh.
These terms don't have big G in it, so we can't
Oh,
quite
okay.
get rid of it. Yeah, in terms of canceling out that way, because we've gotten rid of the only thing that's common to every term. But there are some things that will be equal to 0.
Velocity initial would be 0?
No, we are starting it out when it's going whatever that maximum speed is. We're starting out with that. All right, so this is still going to stick around, so we'll write that down. So that's still around. Let's think about this. This thing is gonna keep going and going and going.
This equals zero because V at the surface.
V at the surface is not zero. That's the maximum speed. That's what we're trying to find. We want to find, I guess I should write max here. We're trying to find that maximum speed so that this thing never returns.
The R,
Which one? I have an RI and an RF.
RF,
Why?
cause it's not coming back, so,
So what does RF become if it never comes back?
Undefined?
I heard two things at once.
0,
Zero, remember R is the distance from center to center. So if RF becomes zero, that means you're saying that this object is at the center of the planet. But what does, you're almost there.
Undefined? Like
No,
it would be infinitely bigger?
infinitely bigger. The denominator here gets infinitely big. So take a fraction, the G, big G is a number, mass of the planet is a number. So this number, if I multiply these together, I'm getting something. Divided by something infinitely huge. So what is some number divided by something infinitely huge? Well, we can work it out if you have to. So let's make G times mass of X. Let's say that G mass of X over R. Let's just say the top is equal to 1 over R. So let's make that huge. I keep adding zeros. What's happening to the fraction as my denominator gets bigger and bigger? So it's not that R goes to 0 here, but this whole thing goes to 0. Because RF becomes infinitely large. All right, we actually have one more thing that goes to 0. It's close enough to count from a physics point of view. Just like this doesn't ever actually equal 0, it's just close enough for a physicist. Well, they have two variables left. Is the initial distance, what is the initial distance? If it were 0, that means that the object is starting out at the center of the planet.
Would be the distance from the center of the planet to the center of the projectile?
That's what R would be, yes. So initially, what is it? You might have been thinking it, I just didn't hear the words. If we launched it from the surface of the Earth, what would this initial R be?
Is that the 6.38 one?
So for Earth, it would be that, or generically, just it's the radius of the planet. So this is minus big G, mass of planet over the radius of the planet. We assume the satellite is so small that it really gets dwarfed out. Whatever the radius of the planet is, plus the radius of our satellite, which we'll assume is tiny. Well, that only leaves one thing left. What else are we assuming is so close to 0 that we're going to call it 0?
1/2, 0.
Yep. So obviously the 1/2 is not, that won't be 0, that's a half. But it's slowing down. As soon as I launch it, the thing slows down. Now it never actually hits 0, but it is getting slower and slower. Because remember, the gravitational pull is getting weaker as this thing goes out. So this is close enough to 0 because VF is approximately 0. It's some tiny number. So after all of that, we are now left with this very seemingly simple formula, at least a lot simpler than where we were before. I have 1/2 times the initial speed squared minus big G mass of x over the radius of the planet equal to 0. So if we solve for VI, I'm just going to bring this over to the other side. So I have 1/2 VI squared is equal to big G mass of our planet over the radius of the planet. Trying to get the VI, so I'm peeling away the layers. First I get rid of all the plus and minus stuff. Now I have to get rid of this 1/2, so I multiply by 2. So VI squared is equal to 2G mass of the planet over the radius of the planet. And so VI, now I have to get rid of that square by doing a square root, 2G mass of x. All right, let's use it. Let's assume Earth. How fast do I need to shoot something from Earth, assuming there's no air resistance and it doesn't crash into anything? How fast do I need to shoot it so that this thing will never return? Well, there's that initial speed, that moment when it leaves the Earth. That's 2 times 6.67 times 10 to the negative 11th times mass of Earth, since I'm talking about Earth right now, 5.98 times 10 to the 24th, divided by the radius of the Earth, 6.38 times 10 to the 6th, not squared. If someone would, actually more than one person, be kind enough to crank through the math. So the formula for escape speed